Hello everyone, I am Siddheshwar Kadam from Department of Mathematics, Bristol and Hyderabad campus, India. I am a PhD student and my area of research is cosmology and theory of relativity. Before start my presentation, I would like to thank the organizing committee of Cosmology from Home 2023 for giving me this opportunity to present our work here. Today, my topic of presentation is Noether Symmetries in extended teleparallel Gauss-Bonnet cosmology. These are my topic outlines. I will start briefly introducing teleparallel equivalent of general relativity. Then I will talk on the mathematical formalism of f of TTG gravity. Then I will give brief information about Noether symmetry approach, and finally I will conclude with the outcome of the study. So as we know, uh, after the discovery of general theory of relativity by Albert Einstein, there are several attempts to obtain modification in general relativity took place. One of the first attempt was made by Hermann Weyl in 1918. The motive to obtain modification in GR was to unify electromagnetism and gravity. With the same motive, Albert Einstein himself obtained modification in GR and replaces the general metric coefficient with tetrad component and define the formalism, which we call it as teleparallel formalism. Since the field equations for teleparallel gravity is similar to the field equations of GR, we call teleparallel gravity as teleparallel equivalent to general theory of relativity, that means TGR. Although both the gravities have same field equations, but there is a difference in interpretation. In GR, we have the Ricci scalar R to represent gravitational interaction, while in TGR, we have torsion scalar T to represent gravitational interaction. In GR, we have Levi-Sutta connection in background, while in TGR, we have Weizenbuch connection as a background connection. To study the phenomenon like dark matter, dark energy, and the inflation, the GR could not able to succeed. That's why there is a need to obtain modification in GR. Therefore, with the motive of studying the properties or the nature of dark matter, dark energy, and the inflation phenomena, researcher obtained modification of teleparallel equivalent of GR also. One of the first modification or one of the initial modification to TGR is f of t gravity. Basically, this modification is similar to the f of r modification of GR. Although the field equations of f of t gravity is of second order, but this gravity fails to obey the Lorentz transformation. Therefore, to study the Lorentz invariance in teleparallel gravity formalism, researcher obtained further modification of f of t gravity and obtained f of TB gravity. The f of TB gravity formalism was first introduced by Mahamoudi and his collaborator in 2015. Here, we have a limiting condition like we will able to obtain t minus b equal to r. That's why, or at that case, one can study the Lorentz invariance in teleparallel gravity formalism. If someone wish to consider whole information related to the torsion tensor T, then he has to consider f of t TG gravity. Also, to study the scalar field effect in the teleparallel gravity formalism, one can consider f of t phi gravity formalism. This formalism or the f of t phi gravity formalism was introduced by Spinoza and introduced it in 2021 year. Let us start discussing the mathematical formalism for teleparallel Gauss-Bonnet gravity. Here we have considered flat FLRW spacetime, which is described in equation number 1. The diagonal tetrals are described in equation number 2. The general metric and the Minkowski metric can be interlinked with each other with their relation, which is described in equation number 3. These tetrads are satisfying the orthogonality condition, and the condition is described in equation number 4. Here, we have used by a Weizenbuch connection, which is described in equation number 5. So one can obtain or one can study the torsion scalar T by or in the form of contractions in the torsion tensor, which is described in equation number 6. And the teleparallel Gauss-Bonnet term can be obtained by using equation number 7. By varying these indices from 0 to 3, one can obtain expression for t equal to 6h square and tg equal to 24h square h dot plus h square. Here, the action formula for f of t tg gravity is described in equation number 9. So to obtain field equations, we have to vary this action with respect to the tetrad, and one can obtain the field equations for energy density and pressure, which is described in equation number 10 and 11. Let us start discussing Noether symmetry approach. All we know, this approach was first introduced by Emmy Noether. The Noether's theorem plays a very important role to discuss about or to deliver information about the conserved quantity. So for an example, if you consider a Lagrangian, which describes a motion of a free particle in a space, if that Lagrangian is invariant under translation symmetry, that means there exists or there must be a conserved quantity corresponding to translation symmetry. And in that case, we are getting the linear momentum as a conserved quantity. So the Noether symmetry, while talking about Noether symmetry, one has to remember the code. For every continuous symmetry in the nature, there exists a continuous or there exists a conserved quantity. Also, Noether's theorem or Noether symmetries allows us to reduce the dynamics of the system, and which will help us to obtain exact solutions. The Noether symmetry approach is also used as or act as a selection of or act as some sort of selection rule to choose a cosmologically viable models. Here, in the literature, the f of t tg gravity formalism in the Noether symmetry aspect has been studied previously by S. Capozziello and his collaborator in 2016. Let us start discussing Noether symmetry approach in f of t tg gravity. Here, we require the Euler-Lagrangian equation that we have described in equation number 12. The Euler-Lagrangian equation for scale factor A, the torsion scalar T, and Teleparallel Gauss-Bonnet term Tg, which is described in equation number 12. The energy condition in this case is described in equation number 13. Here, the Lagrangian with canonical variables A, T, and Tg can be written as described in equation number 14. And this equation number 14 Lagrangian can be represented in terms of the Lagrange multiplier lambda 1 and lambda 2 as described in equation number 15. On differentiating equation number 15 with respect to T and Tg, one can obtain value for lambda 1 and lambda 2. And by reputting the values for lambda 1 and lambda 2, we have obtained the expression which is described in equation number 16. By solving this expression by integration by parts, we have obtained the point-like Lagrangian, which is described in equation number 17. So to check the viability or to confirm the correctness of this Lagrangian, we have backput the obtained Lagrangian into Euler-Lagrange equation for A, T, Tg, and energy condition, and obtain the expressions which are described in 18, 19, 20, and 21. Here, equation number 18 is obtained due to putting this point like Lagrangian into the Euler-Lagrange equation for A, and this equation number 18 is similar to the expression for pressure for f of t gravity. From equation number 19 and 20, which are obtained by putting the point like Lagrangian into the Lagrange equation for T and Tg, we can conclude that the value for Tg is 24h square into h dot plus h square, and T can be obtained as 6h square. The point like Lagrangian, after putting into the energy condition equation, which is described in equation number 13, one can obtain expression 21, which is similar to the expression for energy density in f of t tg gravity. So by this, we have confirmed that our obtained Lagrangian or obtained point like Lagrangian is correct. Here, while studying Noether symmetry approach, one have two methods or two ways. One is Lie derivative test, and another one is Run-Trut identity. The existence of Noether symmetry can be confirmed by obtaining the Lie derivative of the point like Lagrangian. If that Lie derivative is 0, then one can confirm that there exists a Noether symmetry corresponding to that point like Lagrangian. Also, one can confirm that the Noether symmetry or the existence of Noether symmetry by putting the point like Lagrangian into the Run-Trut identity. Here, we have obtained we have put the point like Lagrangian into Run-Trut identity and expand this identity where the expression for x raised to power 1 and the generating vector is described in equation number 24 and 25. By putting point Lagrangian in equation number 23 and by equating both the sides, we have obtained 21 partial differential equations, which are described in equation number 26 to equation number 46. So this is the system of partial differential equation which we have obtained during the study of Noether symmetry. To solve this system of partial differential equation, we have two ways. Either one can construct or one can consider a non-trivial Noether vector which satisfies all those equations and can obtain form of f of t t g. And the other ways, one can consider form of f of t t g and obtain non-trivial Noether vector. Here we have considered, or we have followed the other way, in which we have considered form of f of t t g. Our first form is the sum of separated power law, and in this form, while backputting this form into this 21 partial differential equations, or this system of 21 partial differential equation, we have obtained non-trivial Noether vector, which is described in equation number 47. So by this, we can confirm that this form obeys Noether symmetry, and by putting this form into the point like Lagrangian f of t t g gravity, why we have obtained the form which is described in equation number 48. So by using this form into the Euler-Lagrange equation for Tg and A, we have obtained expression 49, 50, and by putting that point like Lagrangian into the expression for Tg and A, we have obtained this 49 and 50. Further, those expression 49 and 50 are reduced to 51 and 52. Therefore, to solve this, we have, or the exact solution, or to obtain exact solution for this equation 51 and 52 is quite easier than solving those system of partial differential equation. Here, we are able to obtain two exact solutions for these two equations. One is of the form power law, and second is of the form de Sitter solution. From these two solutions, one can study the accelerated expansion of the universe phenomena by obtaining the deceleration parameter. Here, the parametric range for which these two scale factors explain the accelerated expansion of the universe is mentioned on the screen. Further, we have considered two forms. So one of them is minus t plus j into exponential of m into tg. And in this case, we have obtained the non-trivial Noether vector, which is described in equation number 55. And the point like Lagrangian, as described in equation number 56. By putting this point like Lagrangian in the Euler-Lagrangian equation for A and Tg, we have obtained expression for 57 and 58. So it is quite easy to obtain a solution for expression number 57 and 58. Here we have obtained exact cosmological solution, which is of the form e raised to power lambda t. And we can see that there are some conditions on the model parameter m, which are described along with the de Sitter solution. The third form that we have considered in this study is Legendre model, which is of the form minus t plus j into e raised to power m in the root of tg. So while studying the Noether symmetry for this form, we have obtained non-trivial Noether vector, which is described on the screen, and the point like Lagrangian in this case is described in equation number 16. Here, by putting this point like Lagrangian into the Lagrange equation for scale factor and the Tg, we have obtained expressions 61 and 62, and we have easily obtained the exact cosmological solution for these two equations, which is of the form e raised to power zeta t. And here also we have obtained certain conditions on model parameters j and m. Further, let us summarize the results. So in this work, we explored the f of t t gravity formalism in the prism of Noether symmetries. We have used the Runge-Trotman identity to frame the partial differential equations. And to solve those equations, we have considered the standard forms of f of t t. The first form that we have considered is sum of separated power mole, or sum of separated power law model, and confirm that this model is capable to use the non-trivial Noether vector. And in that case also, we have obtained the exact solutions, which is of the form power law and the de Sitter solution. There are other two models also. One is of the form minus t plus j into exponential power mtg, and second one is a Legendre model. Both the forms are successfully capable to describe the non-trivial Noether vector and capable to obtain the exact cosmological solutions. Here, corresponding to exact cosmological solution, we have obtained the deceleration parameter and also described the parametric range at which the late time cosmic acceleration phenomenon can be described. The publication details for this study is already published in Physica Scripta journal and are presented at the bottom of the screen. So thank you all for patient hearing. Thank you.